Jitendra Prasad. Well, he has some unique distinction, I see. Is currently working with Indian Institute of Technology, Ropar, as associate professor, and after graduating with the BTech honors from IIT Kharagpur, he worked with the Indian Register of Shipping at Mumbai for 4 years. Then he did his Master of Engineering at NTU and a PhD degree in Mechanical Engineering from Michigan State University. And very interesting, he worked as a postdoctoral fellow in orthopedics and sports medicine at University of Washington, Seattle. This is something, because now we are talking so much of bridging between medicine and engineering. I think you're already quite into it. Then he joined IIT Ropar and now he's there as the professor in the Department of Mechanical Engineering. He is going to talk on invertible mathematical model of cortical bones adaptation to mechanical loading. So welcome Dr. Jitendra Prasad for this webinar on digital health with the focus on biomechanics, and over to you, Professor Jitendra Prasad.
Thank you very much for inviting me for talk. I'm humbled, actually, and especially given the lineup of distinguished speakers. I really am lucky that I got opportunity to actually talk here. So, is my slide visible?
Oh yeah.
Yeah. Okay.
Yes, sir.
Yeah. So, I'm going to also make it. Somehow I'm able to get. Is it okay if I go ahead without pointer? So
Yeah, should be okay.
yeah, okay. Yeah, so it's basically already Dr. Satish and Professor Deepak have talked about Wolff's law and Frost mechanostat, and that makes my life easier here because actually I work on those areas only. So actually the finding the details about these things. So I have the picture of Popeye with a purpose actually, and we love this cartoon character because he has to just eat a can of spinach and he builds his muscle. So we are not that lucky. We have to go to a gym to build our muscles or take up some sports. So but if we go to like if we take up if we play some tennis, then basically we have to play with both the hands. As you can see with professional tennis players, only playing hand will gain more mass, the muscle as well as the bone actually. So you can compare here. So Victor Troitsky being the right-handed tennis players, his bone mass on his right hand, we can see it is much bulkier than his left hand. And the difference is so much that one of his fans rightly said that he ate his spinach with the right side of his mouth only. So obviously referring to Popeye basically. So this is not only for Victor Troitsky, but also for other tennis player as well. So for Rod Laver, for example, you can see his left hand, that the left arm is bulkier. Similarly, you can see for Rafael Nadal, his left arm is thicker than his left one. Similarly, you can see for Serena Williams too. Right arm, you can see it's has more bone mass like muscle, and similarly for Maria Sharapova as well. So basically, this not only muscle but also the bone also. So there has been studies where researchers have found out that the bone mass actually the bone volume increases like as far as to 28% more than non-playing arm. So, okay, so basically why it happens? Okay, so already Dr. Satish has introduced us to Wolff's law. So this is because bone adapts to loads. And this Wolff's law came because of two prior work, basically. So one was famous anatomist of his time, George Hermann von Meyer. So he actually showed a femur, the slice, the cross section of femur. And then that exhibition was being attended by Carl Kalman. So he was a famous structural engineer of his time. And he readily recognized that the microstructure actually like aligned with the stress trajectories. So, and he used to use a stress trajectory for designing bridges and cranes. So he's both actually published some paper or something, and then Julius Wolff actually he stipulated that this cannot be just by coincidence. So there must be some basically the bone must be adapting to loads basically. Yes, and hence he published his work, and we know it as Wolff's law basically. Yeah, so Wolff's law, just saying that bone adapts to load is a very simple thing, but actually it is it has a lot of mysteries. How exactly it does that? So in our lab, we try to unravel some of those mysteries. For example, one of my PhD students, Chandra, he actually investigated why the bone sections are the way they are. So you can clearly see for this mouse tibia, the bone sections is somewhere it is circular, somewhere is triangular, and even different shapes as well. And you can also see that there is some eccentricity basically. So that means you can see as the bending moment increases, so does the area of the bone and the moment of inertia of the bone. So this is example of adaptation only. So not only this spatial adaptation, there is also temporal adaptation. As we grow, then our forces also change basically. Yeah. So as Dr. Satish also showed in case of a spine. So for long bones also, the type of forces that we experience keep on changing, and so does the cross section of the like femur like tibia and femur as well. So for example, when we are just after the birth, the bone at the mid the diaphysis tibia is almost circular, and then it becomes more triangular as we grow. So this also tells us there is some kind of adaptation going on. So this is being adapted for more bending in later stages. Okay, so already Professor Deepak has talked about the space flight and how bone disruptions happen. So this is also a part of, so basically Wolff's law only. So Wolff's law not only tells about bone gain or shape change, but also our bone will resorb or there will be bone loss when there is a unloading. Yeah, so already we know from Professor Deepak's talk that the astronauts lose as much as 2% bone mineral density per month at hip. Okay, so and hence they carry like they take biophosphonates in a space and do cycling type of exercises. Okay, so and this is because of the this Wolff's law. It was very simple. It just said it bone adapts to loading, but why it adapts, it did not tell us. So later on, a lot of work was done during the 19th century, and thanks to like Harold actually. So this he devised along with his group the Frost mechanostat, and we also call it Utah paradigm. So one of the things there is this mechanostat says that there must be two thresholds, the lower threshold and upper threshold. So if the strains or some kind of a stimulus, if it is less than lower threshold, there will be a bone resorption. If it is more than the upper threshold, then there will be new bone formation. Okay, so we also know today that the dynamic load is very important for new bone formation. Okay, and this is because due to dynamic loading, there is a fluid flow happens inside the bone, and which is sensed by osteocytes, and there will be some stimulus generation of some biomechanical signal which would eventually reach osteoblast, and osteoblast will form new bones. So this is very this is, I'm telling in the, actually this is a very shortcut. This is it takes a big molecular cascade it has, but this is just in nutshell it is like that. Okay, we also know that there are the loading parameters based on which we see the new bone formation. New bone formation depends on the loading parameters. So loading parameters, when we say, then the loading waveform, whether the loading is rectangular or sinusoidal, number of cycles per day, and total number of bouts of loading, so, and time between loading as well. So this has been like studied in experimentally as well, and there has been different kinds of loading as well. So it started with 4-point bending, and then there was axial loading model we have in the literature, then the cantilever bending as well, then 3-point model as well. However, it is not very simple, because if you see the bone formation due to all the due to all this kind of loading, then you will see that they not always follows a certain like pattern. So sometimes a new bone formation will be on the neutral axis, sometimes it would be away from the neutral axis. So actually our lab was first to actually compare 4 different loading conditions. One of my PhD students, Abhishek, actually he compared that. So basically, that means it's not that easy, So we got motivation that we should dig further. What is the reason behind it? Okay, regardless of where the new bone forms, in all those experimental studies, one thing was common, that they quantified the new bone formation, and we need to know, because we propose the model based on this quantification only. So basically, what you see here is a cross section of mouse tibia, and the outer cross section, which is like periosteal surface, can be divided into 2 parts. One part, you can see where you see the green ones. This is the new bone formation. So let us say the length of this circumference is C1, and the other part is C2. So where there is no bone formation. So total circumference becomes C, which is equal to C1 plus C2. So bone surface means the whole circumference. The mineralizing surface, MS, is equal to C1. That is the surface over which, or the circumference over which the new bone has formed. So there is one quantity called MS over BS, or mineralizing surface over bone surface, which is equal to C1 over C. Then second quantity you will see in all the paper is bone formation rate, BFR, which is total area, new bone area, divided by the total circumference, divided by the number of days for during which this new bone formation has occurred. Okay, so this is average over the whole circumference. Okay, the third quantity is mineral acquisition rate. So there, so instead of averaging this for the whole circumference, the MAR tells average it over the mineralizing surface only. So basically A divided by C1, that is the length of the mineralizing surface only, divided by time it took to deposit this area. Okay, and then one more thing, site specific MAR. So that we are just saying that you measure the thickness at a point where the new bone formation is, and you divide it by the number of days it took to grow this much. So I'm going to use these quantities. Basically, that's why I took time to explain this one. Okay, so I'm going to propose like two models. One we will call it average BFR model. So this will predict the total new bone area only. Okay, so we are not concerned about where the new bone occurs, as long as our model predicts the total area. We are fine with that. Second is site-specific MAR model. So where we are not only concerned with total area, but also concerned with the distribution of this area, where it happens. So we want to have the newborn grown exactly where in the experiment it is. Okay, so then so before we proceed, we had to like find out whether there was any existing BFR model. So the idea was to actually find very simple straightforward model in which you just put value of strain magnitude, a number of cycles, a number of days of loading or waveform of loading, and then it will give you some BFR value, means the area itself. But we could not find any such model in which there is a direct relationship between that. So we are looking for some equation that will give us. Rather, you would find some site-specific MAR model. So it will give you in terms of the rate. So here M is the bone mass basically. So rate of change of mass is equal to a constant multiplied by some stimulus and minus some threshold basically. Here a stimulus could be have been suggested different by different people. So typically this is a combination of a strain or a stress or a number of cycles, so there has to be some power in, and so on. Or it can also include some frequency as well. Okay. Well, so we tried actually these things actually, and just to know whether it works or not works. We took like some example in vivo problem, tried to do it when we could not actually like successfully apply the existing models. Then we also try to my student also try to include some more like stimulus, for example. So for example, we also included shear strain, shear because of bending, and like shear stress due to the like fluid flow. Okay, we were able to actually predict or model that, but that required a different threshold for different surface, like in tensile like surface, there would be different threshold. At compressive surface, it would be different. Similarly, at endocortical or inner surface, the threshold would be different, and so on. So it was not elegant. Yeah. And also we tested for only one kind of loading, that's a cantilever bending, and we wanted to actually do it for all different kinds of like loading as well. Okay, so basically to sum up, we actually found out the limitations of the existing site-specific MR models. So each of these models was tested for only one loading condition, that is axial cantilever, 3-point or 4-point, and so on. So that means these existing models were not robust, and most of the existing models predict like MAR monotonically or linearly increasing with respect to stress, strain, or frequency. So that means it cannot predict bone formation at neutral axis. As we know, at neutral axis the strain is 0, hence there will be no new bone there, but we find that in some cases new bone is there also. Also, it wrongly under predicts bone formation when rest is inserted in the loading waveform. Okay, so what is the meaning of that? So meaning is this. So this is I've taken from one of the papers from the group where I later did my postdoc from, so University of Washington in Seattle. So in one of their work, when a cyclic loading continuous loading was given to mouse tibia, then there was very little new bone formation. But if there was a 10-second rest inserted between two cycles, then there was more new bone formation that you can see here. So basically, this needed a different kind of thinking. Just for example, some viscoelastic model I thought of based on this. Okay, so that means there was a need for a new model. So a robust model that predicts a new bone formation for all kinds of loading conditions that we needed, and we needed to incorporate rest inserted between loading waveforms. Also, we wanted a model. Excuse me. Okay. So we needed a model that incorporates rest inserted between loading waveforms, and that predicts overall bone formation rate, and also predicts site-specific mineral apposition rate, and can also be inverted, meaning that if we specify the MAR, desired bone growth, then it should also give me the forces that would induce this one. And there was no such existing model, so we started working on that. Okay, so we proposed this model. So we said this is the average BFR model. So this is true for the whole section basically. So the idea was to get the total area without giving any respect to where the distribution of that area. And we proposed that this BFR, bone formation rate, equal to a constant multiplied by differences peak strain at that section minus one strain threshold, multiplies by xi, where xi becomes a constant for a section for a given waveform. So where xi will be a function of the viscosity, because we would consider the viscoelastic model, and this will equal to del like epsilon. So del epsilon basically is nothing but the peak to trough like amplitude of the strain divided by peak strain. Peak strain becomes the peak strain, the maximum strain basically, magnitude wise. Okay, multiplied by n to the power q, where n is the number of cycles of the waveform. Q is a constant. D is so this is a number of cycle per bout, and multiplied by d to raise to the power of beta. So d is the number of like days it was loaded. Okay, beta is again the constant. Okay, so then as I said earlier, so we assumed the material to be viscoelastic for obvious reasons, so that we could predict the rest inserted loading basically. So and then we took data, in vivo data. So in vivo data based on one of the work I was involved with while I was a postdoc at University of Washington and Seattle. And this data we took to fit our model, and we got the model parameters. Okay, so basically the based on this model parameter that we optimized to get, now you can see the predicted BFR by the model in comparison with the real in vivo studies data, and you could see that the BFR are actually close to the in vivo or experimental data. Okay, so once we have that, then we thought about the site-specific model. So site-specific model required like simulation of like the stimulus like diffusing through the osteocyte osteoblast network. And so we assumed the stimulus at every osteocyte to have the similar expression as we used for BFR model. Only difference was, instead of taking the peak strain for the section, we took the peak strain at that location only, at that at that particular osteocyte only. Okay, so for different osteocyte, the value of this like epsilon I peak would be different. Okay, so that like each osteocyte will have different stimulus, and those stimulus also could diffuse basically. So and we apply the Fick's law, and this stimulus like in terms of like in form of some biochemicals would reach the osteoblast, and we assume that the like mineral apposition rate is proportional to the flux of the stimuli at that osteoblast. Okay, so we did the 1D finite element analysis for this diffusion, okay, to get those like flux at those osteoblasts. Okay, okay, and then we like fit the data, and again we took the same paper that we took for the BFR model, and like as you can guess that MAR model, that is the distribution of area, can also give us the total area as well. Okay, so that's what we actually compare the total area as well first, just to see for different protocols, because the site specific results were not given for all protocols, only for one protocol was given. So so we try to match BFR for like all given protocols, and for the given site specific data also we try to match. So you could see that this is the one of the six like one of the for one of the protocol, the new bone distribution was given, and our result is close, basically not exactly where, but I would say it is close to the in vivo results. Okay, so once we got those model parameters, then we now try to solve different kind of loading now. Okay, we got the we fit the model, and we got the model parameters, and the next was to just predict some for some different kind of loading. So we took the axial loading. We took 3 examples basically. So out of the 3, 2 had like site specific new bone formation given. So we tried to simulate that, and you could see here the experimental on the left side, and the actual model, the new bone formation, is given on the right side. Okay, so these are 2 conditions. So these are, you could see the regions where the new bone formation we could predict it. Okay, so the third example of axial loading, unfortunately for this one, there was no site-specific section shown, so we compared it by total area rather than the area distribution. So you could see that total BFR is actually close to the experimental values. Okay. Okay, so for we got more details about all the parameters for our model, and we also tested 4-point bending as well. And however, for 4-point bending, there was no site-specific data available, but it has the total area given. So we actually compared the total area only, and you could see this is actually roughly the same. Okay, so once we got this BFR model and the site-specific MAR model, the next was to invert it, meaning that if we have given the total area and or and MAR value, means area distribution, whether we can like predict the forces like axial force or bending moment and bending moment that would give the this kind of MAR or BFR. Also, the variable here was the forces, the axial loading and bending moments in 2 directions, and we had to match the total BFR or total area, or we can also compare the area distribution as well. Okay, and here the idea was to minimize the squared some squared error between the model values, model results, and the actual in vivo data, basically. And we did that, and we try to predict for one of the like in vivo study reported in the literature. So we gave new bone formation as shown in the figure for periosteal new bone formation, and we could get a similar new bone formation in our model. And for that, we predicted the forces that would be needed to get these new bone formation, and we found that the maximal tensile strain and maximum compressive strain at that section that would be needed to give this new bone formation were close to the in vivo values. Okay, so there was also some limitations. So one limitation was we could not predict the endocortical new bone formation. You must have seen we compared. You might have the question already probably that we did not compare the endocortical bone formation, and this is because it's much more difficult because this is close to bone marrow, so it's a lot of activities happen there. Also, there's a lot of bone resorption. So while the mice are young, the new bone formation happens on endocortical surface, but when they reach adulthood, after that they have bone resorption mostly. So this is complicated basically. So we have taken as a future work. Also, we could not like predict the woven bone. This is also because lamellar bone and like woven bone have a different biomechanical mechanism to make them, or because of that, basically we could not achieve that. So we have taken that challenge though. So in future we have plans to actually study them. Okay, so to conclude, we actually built the first simple mathematical model that can directly relate BFR to loading parameters, which may help orthopedic surgeons. This is the first invertible site-specific model, first model that works with or has been tested for different kind of loading. So earlier models work with only one kind of loading. Okay. So we have related publication actually in scientific reports, and this work is also based on my PhD student Ajay Goyal, and this work was actually was featured on SBMR's Facebook page and on Twitter as well. So I'm thankful to them. But I take it as recognition, especially because I'm not associated with SBMR. SBMR stands for American Society for Bone and Mineral Research, and I acknowledge funding from DST, Science and Engineering Research Board. With that, I thank you very much, and any question is welcome.
Thank you, Professor Jitendra, for that very insightful presentation.